Thanks very much for the introduction. Yeah, I think it's just important to stress, by way of introduction, it's an unusual setting that I find myself in because I'm not an occupational hygienist. I'm just an engineer. Um, but really, my passion for this topic really has been with me for quite a few years because my career started out very much being very conscious of dust and its impact on health for my time working with fly ash as part of my PhD, and then when I worked in power generation. So it's just somewhat fitting that I've come across this topic whilst working in the construction industry, and particularly whilst working with Hilti, which has had a number of these systems in place to manage silica dust in the construction industry for quite a few years, and I've been lucky enough to work with those systems for quite a few years. So what we're going to be covering today really is this overall topic of dust control in construction. So broadening the whole discussion outside of just the stone benchtop manufacturing industry into construction as a whole, because it's a fairly significant issue in the greater industry. And in particular focus in this presentation is what are the implications of the new working exposure standard for silica dust in the industry. And I have a feeling that the industry doesn't really have a strong feeling yet of what it needs to do to deal effectively with the new working exposure standard. And hopefully, with some of the knowledge that's shared during this presentation and with your expertise, we'll be able to push the message out there a lot more effectively. So what we're covering today really is just a bit of background on silica dust. Precisely what are we dealing with, and then go into looking at what are the implications of the new working exposure standard, some alternative technologies that we can use, not just standard control measures of engineering controls and RPE, but can we substitute technologies with new technologies? Then we'll go into the engineering controls themselves and what are their effectiveness, and then finally we'll cover off some important part of the whole engineering control system, which is the vacuum cleaner, the component at the end of the chain, which has also got some idiosyncrasies attached to it that I think everyone needs to be aware of, such that we can make them as effective as possible in the whole dust collection process. And during the presentation, we're going to activate a few polls along the way, just to keep it interactive and just to test that the message is getting through, which certainly helps me in the future for tailoring the presentation. And I'll alert you to when those polls are happening, and they'll pop up on your screen. And also, feel free to type in questions along the way, and if I'm able to, I'll answer them. Otherwise, we can also answer questions right at the end. Okay, so silica dust, the big topic. What does it actually look like, and what is it? Being hygienists, I've got no doubt you're across the mineralogy and the chemistry of respirable crystalline silica dust, and really, it's the crystal, it's the mineral of quartz. But seeing it in practice is actually, I think, quite a good thing, because it's really good to know what you're dealing with. Because when we just look at silica dust in the workplace, on a construction site, or in a manufacturing plant, it just looks like fine powder. But really, when you look at it in the undisturbed state, we can see, and those are the pictures in the center of your screen. They just really look like little rocks. That's essentially what they are. And when they are disturbed, when I say disturbed, I mean when they are disturbed by the action of cutting or grinding or breaking or drilling, they simply break up into smaller particles. They fracture along their cleavage planes, and they become simply smaller, sharp little rocks. And when we've actually recovered them we've looked at them in the electron microscope, once we've recovered them out of P2 dust masks, it's quite interesting to look at their shape. Although they do become smaller rocks, nevertheless, because they've cleaved along their crystal planes, they become smaller, sharper rocks, which means that a freshly cut silica crystal or quartz crystal is probably causes a greater inflammatory response than a more mature, slightly more rounded, larger particle. So this is really what we're dealing with. Now the thing is to realize as well is that silica is probably one of the most common elements in the Earth's crust. I think it about nearly 60% of the Earth's crust is made up of silicon dioxide. So no matter what you do in construction, you're going to come across it in some way, shape, or form. And in the next slide, we actually look at just some of the proportions of crystalline silica that we see in different construction materials. So on the left hand of the screen, you see like a ranking of typical construction materials that have the highest crystalline silica content down to the lowest. So engineered stone consists of upwards of 93% crystalline silica, and that tails off through sandstone, brick, fiber cement board, concrete, and plasterboard. And natural wood has very little crystalline silica in it. Now, when we look at the sources of dust, or how it's really generated on construction site, it's helpful to divide it up into two portions, really. Firstly is the primary generation of the dust, and secondly the secondary generation, because these are two scenarios that are dealt with quite differently, but contractors have to get in control of both of them. So the primary generation is when you're actually disturbing the engineering material, when you're disturbing by cutting, drilling, grinding, or breaking, and that generates a lot of dust, particularly during cutting operations if it's uncontrolled. Now you can control most of that through engineering controls, but the dust that escapes, that settles on other sources, and that can be disturbed if you walk over it, drive over it, and if you use a broom, because that simply elevates it, and that's the secondary dust source. So primary dust needs to be controlled by engineering controls, and secondary dust needs to be controlled by a combination of administration controls and engineering controls. I want to talk about this topic of I think I just alluded to it. I referred to elevation. Now it's pretty scary when you look at what happens with a particle of dust aerodynamically once it is liberated from the source material. So when you see a contractor working on site or in a workshop, you see them cutting the operation. They're sort of pushing their grinder along with their mask on, and the first thing they do when they switch the grinder off is they take the mask off. It's not a good idea, because the finer the particle is, the longer it takes to settle. So for example, in this plot on the right hand side of your screen, you can see like a range of the size of dust that you'll see on site, and it ranges from say 0.1 micron to over 100 micron. So less than about 20 micron you can't really see, unless it's in a cloud. I mean, they're really small particles. But the important thing that people need to really realize, people who are working with these materials, is it takes a very long time for the fine particles to settle. So a 1 micron particle, for example, will take up to 7 hours to settle to settle 1 meter once it has become elevated. So you can be working in a dusty environment for the better part of a day. Even if you've only done your cutting work in the morning, your environment can stay very, very dusty. So that is an important consideration when putting administration controls in place and when educating people about the importance of wearing masks and how long you have to wear them for, and how you need to handle them. And I always find that when I do these presentations to contractors, this is the one thing that often shocks them, because they think that you only have to worry about it whilst you're doing the machining operation, whilst you're cutting, drilling, grinding, or breaking. But the truth of the matter is, you have to think about the time after you've completed this operation. So I'll pause here very quickly to ask you the first poll. This is just to keep you engaged in the presentation. And the question for the poll is, what is the time taken for a 1 micron particle, or silica dust particle, to drop 1 meter in elevation? How long will it take? Well, it's very impressive. It just I asked this poll across a range of audiences, and this is by far the best result that I've seen. Yes, it takes a long time. It takes 7 hours for a 1 micron particle to settle 1 meter. It's a very scary statistic. So thank you for your participation in that poll, and now we'll move on to the following slides. Back one slide, sorry. It's important to kind of get an idea of the scale of the issue that we're dealing with in construction when it comes to respirable crystalline silica dust, because no one really within the industry has an idea of what these different machining operations generate in terms of dust. So when we look at a range of applications from slitting to lay piping, drilling to put in rebar or anchor fastening points, or concrete cutting or concrete grinding, they generate a lot of dust. So these are just the applications in your screen. You may recognize many of them. But how much dust do they generate? Well, it's a lot. If it's uncontrolled, it's a lot. So just drilling a really big hole, hole after hole after hole on a big construction site, you can generate up to 9 kilos of dust in 1 hour, continuous drilling. Now, it's unlikely a person's going to be drilling continuously for 1 hour, but over a course of the day, it is likely that they'll have about an hour of switch on time for drilling. Concrete grinding, even with a small 5-inch concrete grinder, people can generate up to 3 kilos of dust per 1 hour period. So that dust's going to go somewhere. It's going to go into the surrounds. Much of it will just fall onto the floor, and clearly there's a danger of people drilling it in, of people breathing it in. So really the takeaway from the slide, it's a surprisingly higher number of dust that is generated for any of these machining operations. So you can combine all of these operations that may be happening on a construction site on one particular day, and it's an enormous amount of dust that is generated. Now that's just the sheer sort of kilos of total dust. But what about the concentration of dust within the respirable range if there are no engineering controls employed whatsoever? Now, I pulled a lot of this data out of the CPWR's exposure control database in the US, which is a really valuable resource. And you can see in environments such that of like the heavy drilling that I mentioned, or the concrete grinding, and we can get dust concentrations that are many times higher than the current working exposure standards. So just simply concrete grinding, when we look at our current working exposure standard of 0.1 milligram per cubic meter of respirable crystalline silica dust, if it's uncontrolled, that can easily be many times higher, up to 8 to 10 times higher if it's uncontrolled. So we can really take away from this slide that any machining operation on site, be it drilling, grinding, cutting, or breaking, anything at all, if it's uncontrolled, will be well above the current working exposure standard, and even worse for the future working exposure standard. So the central message is not controlling dust on site is just simply it's not acceptable in any way, shape, or form going forward. So with all of this in mind, I think all of the reviews that have that have been done over the past few years have come to the very sensible conclusion that the working exposure standard does need to change from the 0.1 mark that it has been for many years to the 0.05 milligram per cubic meter place. But there's an enormous amount of work to do to get it to that space. When you see the kind of practices that are going on within the construction industry, and allow me to flick back a slide, and you see the kind of levels of silica dust that are present when there are no controls in place. So there's a lot to do to get us to that new working exposure standard of 0.05. So I'll pause for a moment to ask a very easy poll, and we won't have to spend much time on this, but the question for the poll is, what is the new working exposure standard that will be rolled out in many states? And it was an extremely quick response. Yes, everybody pretty much has got the new working exposure standard is 0.05 milligrams per cubic meter. But we all know, sitting in this forum together, that the actionable level is 0.025 milligram per cubic meter, and that makes it even more challenging. Is that acting from a 0.025 place means that we have to have a lot of controls in place, but also that RPE is just about mandatory in all of these applications to get to that 0.025 level. Okay. So let's compare, the old working exposure standard and what common practices are to what practices will need to be with the new working exposure standard. So in many of these drilling, cutting, grinding operations, the practical thing to do to get beneath the 0.1 or get close to the actionable level of 0.05, the most common thing to do was to just issue a P1 or a P2 dust mask. Now, what was the impact of that? Let's assume that it was fitted properly, and it was and the person is cleanly shaven, and everything was ideal in terms of the fitting of the dust mask. If we use the assigned protection factor of 10 for a P2 mask, it would take the grinding kind of concentration, the grinding concrete concentrations for a small grinder from the 0.83 mark down to 0.08, which is above the actionable level but less than the working exposure standard. So maybe call that a yellow light. With something like chiseling or braking using a jackhammer, it would get it from the 0.3 milligram per cubic meter mark down to 0.03. So that's probably okay. But things like heavy drilling and cutting with electric or petrol saws, even when wearing a dust mask, will still nowhere near getting beneath the working exposure standard. Now, with the new working exposure standard, even if a person was using a well-fitted P2 dust mask, really no one is even near getting close to being beneath the working exposure standard or close to the actionable level of the working exposure standard. So this is the kind of the sea change that I was alluding to earlier, is that going forward, contractors are really going to need to adopt upgrades of technology in the form of engineering controls, or switch technologies to substitute some of these cutting, grinding, or drilling operations to stay beneath the working exposure standard and close to the actionable level. So it's a real, the new working exposure standard, in short, is a real game changing event in the construction industry. And it's something that contractors are starting to come to terms with. So we'll pause again for a quick minute just to ask our third poll. And the question for the poll is, what is the protection factor of a P2 dust mask? Yes, and it is a trick question. It's funny watching the results of the poll on my screen, because it is like a worm. Initially, it's tempting to think that yes, it's a 10 times reduction factor, but the correct answer, it's a 10 times reduction factor only if it's fit tested, because the variables outside of that are just you could get any amount from almost very little protection to quite a good protection, but these masks, yeah, they do need to be fitted. So really, let's start off now the second phase of this presentation, which is really talking about alternative technologies, starting at the top of the hierarchy of controls, and then moving on to the engineering controls that can be employed. So fortunately, there are many alternative technologies available to help mitigate the impact of respirable crystalline silica dust. The first one, which is a good one, is people can switch to wet coring instead of heavy drilling. So instead of drilling a 28 millimeter diameter hole in concrete with one enormous drill bit with a combi hammer drill, they can actually gently core it out with using wet diamond coring. So much of the dust is suppressed. And coring, by definition, you're cutting a very small amount of concrete, because you're cutting a hole like that instead of a hole like that. In other words, you're not removing as much volume of material as you were if you're just drilling it out. So that's a very practical example of what you can do to mitigate dust when heavy drilling. Other alternative technologies, when contractors are putting up small fixings, instead of drilling and anchoring, they can shoot in fixings, which has got a much smaller dust emission than drilling and anchoring, and it's quicker. Instead of drilling and anchoring, contractors can also use casting technology, so that when they're laying the concrete down, they put a cast-in channel in place, and when they strip the formwork away, you have an anchor point that's ready waiting for you. So there's no drilling required at all. So it's like a zero dust emission type of scenario. So there's just a few examples of engineering controls. So this is time for our last poll, and then we'll just move through the remaining slides. And the question for this poll is really, what's a good example of an alternative technology to heavy drilling in concrete? Okay, great. The audience is completely into this topic of switching technologies, and yes, the answer is diamond coring is a great way of mitigating dust when it comes to heavy drilling. And these are always questions one can ask a contractor when doing reviews of their current practices: is what alternative technologies have you assessed? Have you looked around personally? Have you engaged your current suppliers to ask them what are different ways of doing things? Because we never want to tell people, we never want to tell them how to do things. We just really want to challenge people to think about how they're doing things a little bit differently. Now, where the industry is at and where the industry can make the most rapid changes with the least disruption to their business, and in fact get quite strong productivity gains, is employing engineering controls to suck up dust whilst you're drilling, cutting, grinding, or braking. And these are the controls I'm going to flick through quite quickly now, and then move on to how effective are these controls. The first one we look at really is what we can do with exhausting dust during cutting. Cutting of concrete, cutting of brick, cutting of sandstone. We can attach dust hoods to grinders, and these need to be then fed to vacuum cleaners. So it's a good time in this presentation to pause a little bit and talk about like what is the different impact of these systems, because really, putting a very good quality vacuum cleaner of the correct class at the end of your cutting system is only one of the steps. We really need to look at the system as a whole. How effective is that dust hood? Is the insert or the cutting blade that's matched to the insert of the cutting blade matched to the hood, and is the machine and the hood, is it matched to the vacuum cleaner? So we kind of need to get a good idea that all of those components are working in concert. So no matter what supplier the contractor is using for their tooling, it's a pretty good idea that they use a tested system as opposed to cobbling together many different systems and hoping for a good result. Engineering controls for cutting mineral materials. It's good to mix in wet cutting into the mix, with the knowledge that wet cutting doesn't necessarily take out the dust exposure 100%. It certainly dampens it down a lot, but it does not remove it entirely. And I think we've all driven past job sites, and we've all driven past roadworks where we see the classic picture of a contractor using a petrol saw and a person standing next to them with a watering can, trying to dampen down the dust that's emitting from the saw. And it's completely ineffectual, and not only ineffectual in terms of dampening down the dust, but it's ineffectual in terms of productivity, because you've got two people working away instead of just one. Really, the way to go with wet cutting systems is making sure that there's an integrated water supply system, either on your electric cutter or the petrol saw. And as the industry, I think what we really need to watch out for in the industry going forward is people using homemade remedies to equip electric cutters with water supply systems, or equip their existing petrol saws with water supply systems. And it's really, we don't want to replace one health issue with a safety hazard. And it's really a better idea to upgrade your existing technology with technology that's actually designed to operate with a wet cutting system, as opposed to doing any of your own modifications. Wall chasing, particularly in residential estates, generates a lot of dust, because often it's done when the house is complete and people are working in an enclosed space. So with wall chasing, using machines that are actually designed that are dedicated wall chasers is a pretty good idea, and that gives you a good outcome. And the thing that you can notice there is that in these designs, it's always the insert or the cutting blade is almost completely enclosed within the machine itself, and that allows the dust capture to be a lot more effective. A major activity on any construction site and in any renovation site is concrete grinding, or grinding during tuck pointing, during when you're putting up an older building. And this is an engineering situation that is very easily probably one of the easiest to control, as long as the machine is designed accordingly. Things to watch out for really when you're looking at contractors' equipment is is the hood well fitted to the machine? Is it intended to be fitted to the machine? It's not a sort of I dare say like a universal attachment, but it's clearly something that is intended to be in place. And the key piece of technology that's used is what's called the skirt to the hood, and it really can be a system where of bristles or plastic louvers that brush against the surface of the material that you're machining to get a really tight air seal between the grinding blade and the surface. So again, it doesn't allow any dust to be to kind of escape that dust hood. And then we can see in light drilling, many suppliers have onboard dust extraction systems. And then when we get into heavier drilling, there's larger diameters that many builders or civil contractors would be using. You can use a technology called hollow drill bits. So what you see on the left of your screen, it's not a tube, it's actually a drill bit that is hollow. So it's got the classic drill bit tungsten carbide head to it, but then it's got two tiny ports that are machined into the drill bit itself. And then a vacuum cleaner is attached to that red piece that you see, and it sucks out dust whilst you're drilling. And it's got a very good secondary effect as well, is if you were using that hole to glue in reinforcing bar, for example, afterwards, or an anchor, it's already sucked all of the dust out of that hole, so you don't need to blow the dust out, which is another dust hazard. So that's a pretty neat engineering control. It's like using a fundamentally different piece of technology to drill a hole. Now, it's important to note all of this as well, and this is something we try and bring to the attention of contractors, is that by extracting dust whilst you're machining, you actually make the operation faster, because dust is a frictional element. And you're also avoiding the cleanup step afterwards, which is a major productivity driver. So really, by aiming for the new working exposure standard of 0.05, you will actually, just by your actions of aiming for that and achieving it, you'll find your workers are more productive, and your business becomes quite a lot more productive because you save on that labor time. You can even put engineering controls in place for your breakers. They're very effective. And we've got technologies in place to suck out dust if you're blowing out holes. But now, how effective are these controls given the new working exposure standard? This is something that we need to look at very carefully, and it probably it gives us an opportunity to emphasize the point that going forward, yes, engineering controls go a long way to controlling dust. We need to play this in concert with RPE. So the first example that I showed you of dry cutting, it is a difficult application to control. So hence, most contractors are really trying wet cutting where they can, but when you can't, the kind of testing that we've done in our labs in Germany have shown with a continuous cutting process, working away very hard for an hour, and we use a European test standard to make sure we do this consistently in an enclosed space, a 200 cubic meter enclosed space. You're looking at a respirable crystalline silica concentration of about 0.3 milligrams per cubic meter. So it's way higher than the actionable level for the new working exposure standard. So really, when dry concrete cutting, the user doesn't really have a lot of switch on time available to them to be doing this operation. So dry concrete cutting can really only be seen as something that you can do for a very short space of time. And if it's going to be done for any length of time, really we need a more wholesale switch to wet cutting, either by wet cutting with electric cutters or wet cutting with petrol cutters. With concrete grinding, you can get a lot more success out of capturing dust, and we see dust concentrations again in that enclosed space of about 0.04 milligram per cubic meter after a 1 hour period. Now that's 1 hour of switch on time with no air circulation. When working on a construction site where there is some amount of natural ventilation, clearly there would be a dilution effect. So the worker would be okay when we're wearing a P2 mask, but then this raises the point, well, what is the contractor doing to manage the environment? Are the people who are working nearby, are they also wearing masks, or do they have further dust capture mechanisms in place to try and pull down the concentration or disperse the dust better by using forced ventilation to the site? And we've seen contractors do a really good job of combining the engineering control, the RPE, and the dispersal. So we saw that in a site not so long ago in the Gold Coast, where they were using these types of machines, well-fitted RPE, and making sure that the entire floor that the workers were in was ventilated using fans. So those are some of the controls that people can use to keep dust concentrations low. Using on-tool extraction, we're also able to get quite good levels. And again, this is in a confined space, drilling continuously for an hour, really doing the work that a person is going to do when they're actually not just drilling, but they would be drilling and then fasting something or hanging something up. So this drilling 75 holes a day, it kind of reflects the number of holes a plumber or an electrician would be drilling on a full work day on a job site. So these are the kind of concentrations that you would be expecting to encounter. But even this kind of on-tool extraction, really to be well within the new working exposure standard and close to the actionable level of 0.025, we'd really need to be thinking about wearing a dust mask in this operation. And in a very similar story with the hollow drill bits, when we get to drilling those large diameters in enclosed spaces, clearly there's a strong need to use respiratory protective equipment in concert with the technology. So that really is the kind of data that we have available to us to look at how effective are these controls. Before I go into the discussion about the vacuum cleaners, we've also just accessed a fairly significant amount of data from the German construction insurance institution, which is called BG Bau. I won't say the full name of it, just simply because I'm unable to. Where they've got a wealth of tested systems, where they look at the respirable dust levels relative to the European standard. So that's going to allow us to benchmark a lot more of the questions that we get asked from contractors. Will the system be okay? Will the system not be okay? But it only allows us to give a kind of a go or a no-go answer. And fortunately, when you put the respiratory protective equipment protection factor to those numbers, you can give a very good indication as will you be okay relative to the new working exposure standard. So that's that'll be something that we release in the coming months. Now the big topic of vacuum cleaners that I'd like to spend a few minutes on, and just emphasizing the point that I made earlier on about vacuum cleaners. They are just one part of the three parts that we need to be looking at. We're looking at engineering controls to control respirable crystalline silica. The dust hood or the insert drill bit or the grinding wheel. They need to be designed with dust extraction in mind. The tool needs to match the dust hood and the grinding insert or the drill bit, and then we get the vacuum cleaner. So we have a fantastic vacuum cleaner, but a useless dust hood. We may as well not have anything at the end of it, such as the impact. So they work very much in concert. Now, there's a few important things to realize about vacuum cleaners, which contractors often miss entirely. The first one is whether you're using an M or an H-class vacuum cleaner. So M-class vacuum cleaner in the construction space, H-class vacuum cleaner within the engineered stone space. People really need to keep a very close eye on the condition of the primary filters in these machines. And it's something that is grossly overlooked. You know, people have the view, I've bought this piece of equipment and now it's essentially a box that works. I empty it when it's filled, and that's all I have to do with it. And really, vacuum cleaners need care and attention. Their filters need to be inspected regularly, and they need to be exchanged pretty regularly. You can detect when their filters are worn out because the vacuum cleaner is not as effective as it used to be. And as soon as that filter has got cracks, nicks, and bumps in the seal that surrounds it, it's not going to be as effective as it normally is. And we really recommend that, regardless of what they look like, that you exchange filters according to your supplier's instruction manual. And you can get really smart with this if you're a contractor by keeping track of this with your asset management systems. But it's something that really needs to be looked at very carefully. So that's rule one with vacuum cleaners: taking good care of the primary filter. And I was on a fascinating experience exchange call a few evenings ago, and my Hilti colleagues in Sweden were telling us that in Sweden, it's mandated for vacuum cleaners by law. You have to exchange their filters every 6 months, and you have to have systems in place to prove it. If you get a call from a workplace health inspector, so that was quite a significant finding. I was really quite impressed by that. The next rule with vacuum cleaners is collection of the dust, because this is often a control that falls over. I think many of us would have seen what happens on a construction site or what happens in a manufacturing plant. Great care is taken to suck up engineered stone or sandstone in a stonemason's plant, or suck up concrete dust or brick dust in a construction site. And then you see the person whose job it is to empty that vacuum cleaner. They walk out back, take the head of the vacuum cleaner off, and simply upend the vacuum cleaner and get covered in dust that emerges out of the skip, which is not good. It's not a good situation at all. So it's key that bags are used in collecting dust. People can use a plastic bag, or better yet, they can use a fabric or paper bag that can be closed off, and then that bag is just disposed of into the skip. But no more upending of vacuum cleaners, because that just simply defeats the purpose. Then really, finally, what we're doing as a supplier and is within the industry. So you're aware, we do conduct a lot of on-site training sessions, which contractors can request, and we've done a few webinars over the years to try and alert contractors to the dangers of RCS. But I think the real change will be in the next 12 months or so, when people realize that there's no quick fix to getting well beneath the working exposure standard. That one simply needs this combination of switching to an entirely different technology, or using an engineering control and combining that with the necessary RPE. So we taking a very trying to take very proactive steps with that. So that's what we as a supplier are doing in this space. So thanks very much for your attention. For once, I've surprisingly kept within my time limit. I wanted to finish within the hour, so we could leave a few minutes for questions that you can type into the box. And I may not be able to answer all of the questions right now. And if you come up with a question at a later stage, feel free to email me at any time. So now I'm just going to see if there are any questions coming through in the question box.
Thank you, Matt. Really informative. There's now 5 questions in the chat box. We'll start off with the one from Benjamin on local exhaust ventilation. Can you see that?
So I'm just switching to the all chat box. Here we go. Okay. Okay, so I can see a question from Jason. Yeah, the question really is that the UK Health and Safety Labs undertook a review of Hilti's facilities and equipment. The results that I quote there were done according to the EN standard by a third party, because we can only really quote those kind of results by an accredited laboratory. Now, we have got like 2 stages to testing. There's this testing that's done during R&D, and then the equipment then is also supplied to BG Ball for them to do their own testing under those EN conditions, and then we can buy the data back if we want to get the exact numbers. Now, our labs are currently undergoing accreditation to this EN standard. This has been a bit held up because of the COVID situation. So hopefully the kind of testing data that we get in the years ahead will be able to quote the EN standard. But at the moment, any of the data that we put out there, we don't put out any just internal company test data. I think just because otherwise one runs into these kind of questions and these kind of difficulties that you raise here. I'll move on to the next one. Any information on exposure during filter cleaning? No, there isn't. But I did just want to cover that I have seen data from contractors who've actually assessed workers during the course of the day and noticed the kind of spikes that they receive when they're emptying vacuum cleaners, and that's pretty high. And I can only imagine that. Well, I suppose let me answer this a little bit differently. If a person is cleaning a dust filter, which you can, sometimes they clean it with compressed air, which is just a very unwise thing to do, because all you're doing, this is secondary dust exposure, isn't it? Really, then you're just blowing out dust with compressed air into the immediate environment. And if you attack the filter with compressed air, it also damages it. So really, the best way to clean a filter is in just warm, like a warm bucket of water, or gentle running water, but not to blast it. And also the first thing that you see people do when they take a filter out of a vacuum cleaner, when it has those, the corrugated filters, they do this with it like it was a concertina, like an accordion, which again is, filters and vacuum cleaners are not to be manhandled. Okay, then Dina's asked, given the working exposure standard is 0.05, shouldn't class H be for all RCS scenarios, not just engineered stone? Well, this is when we run into that kind of slight constructive tension between a vacuum cleaner standard and what is the efficacy of the overall system. Now, and also, I think the different states differ slightly in their guidance between which vacuum cleaners to use with different scenarios. For example, in Queensland, the code of practice for engineered stone is to use H-class vacuum cleaners, and in other states, it's just specified M or H. Now, when you test the actual system, when you test an M-class system versus an H-class system, even though the H-class looks a lot better on paper because the filter grade is so much higher, it's an order of magnitude better than an M-class. Really, in terms of dust capture efficacy, certainly the internal data that I've seen, I don't want to quote it exactly, it's only slightly better than an M-class. So it just really shows how heavily you're relying on that overall system. Yeah. So I think the really trying to read between the lines as to why H-class is specified for engineering stone. It's just really in that attempt to try and go the extra mile for that very serious sort of engineered stone situation that has been prevalent in our society.
The one from Benjamin about local exhaust ventilation on grinders.
Oh, yes, I've just scrolled down to that one. Yeah. Yeah, Benjamin's asked, it's exhaust ventilation grinders is ineffective when the surfaces are not flat. Yes, it's a stroll. Let's differentiate between surfaces though. If you have a rough surface, if you're using a dust hood that has got a plastic louvered skirt or a nylon bristle louvered skirt, normally it's okay. But where the dust escapes is when you go over an edge. For example, you're trying to grind a fillet on a column, and then you kind of disturb the seal between the skirt and the surface. And that admittedly is very difficult to control. Quite soon we're launching technology that's going to enable us to solve that fillet grinding on columns. But then if it's just simply impossible to control the surface that you're grinding, then one has to switch to looking further upstream to the design constraints. Well, why is it that we had to grind that irregular surface? Is it a formworking issue that needs to be solved? Is it a prefabricated element that came in that was out of tolerance? Why did we need to do that? So it forces the project manager to look further upstream as to like, why were we put in the situation where we had to rectify something to grind it flat?
From Sharon on the capture of very fine particles, and then you end it.
Okay, for some reason I can't
That's
see
okay.
Sharon's.
I'll just read it out to you. Hi, Martin. Would you like to
thanks.
comment on the capture of very fine particles when using water and vacuum assisting cutting?
Yes. Now, unfortunately, that's sort of a new research area for me. I'm aware that a fair amount of research work has been done at the University of Wollongong, which is commissioned by Safe Work New South Wales, to look at how effective exactly is wet cutting. does it remove all of the dust? Does it remove part of the dust? Does it remove just the coarse dust and liberate the fine dust? So the sort of the preliminary stuff that I saw indicated that it removes, about half the dust. But unfortunately don't have a definitive answer on what it does to the fine dust. Yeah, that's a work in progress. So unfortunately, unable to answer that question.
That's okay.
Exactly.
So if we'll just get to Sandy's question. Her question is, any welding specific fume extraction systems?
Could you repeat that question?
Sandy has asked, any welding specific fume extraction systems?
Welding fume extraction systems. Yeah, I'm unfortunately not across that that fume extraction topic at all.
That's okay. Martin, I want to thank you on behalf of AIOH on delivering this fantastic presentation. Everyone attending, our next presentation is on stone benchtops, bushfires, and bushfire emergencies and COVID-19, presented by Dr. Barry Chasson. So once you exit this session, take a couple of minutes to complete a quick survey. Let us know how you found this session and any other topics you are interested in listening to, or if you would like to present on a certain topic, we would be open to those suggestions as well. So thank you for taking out this Friday afternoon and spending some time with us. We'll look forward to catching up with you soon.
Thanks, everyone. Have good weekends.